Hello and welcome to Encore Talks number 39. Today I'll be talking about how to be a great software engineer in the age of AI. Uh, about your humble speaker, I'm Jorge Hernandez. I'm a principal AI ML engineer. I'm part of our AI practice. I've been working as a software engineer for 25 years now. 15 of those I've spent doing AI and machine learning. Uh, and so I started working before the current boom in AI. I've been a research engineer, a manager, a CDO. I've worked with teams distributed all over the world. And yeah, so that's basically me. And today's talk is divided in two parts. First, I'm going to start with what is software engineering, and then how do you become a great software engineer? Okay, so what is software engineering? Like, where does the term come from? The term was coined at the first NATO conference on software engineering that was held in Garmisch, Germany, in 1968. It was one of two conferences. The other one was held in 69. And NATO, the NATO Science Council, organized those conferences in response to what they called the software crisis. In the late 1960s, um, you could start to see that there was a problem when trying to build software. Like projects ran over schedule, ran over their budget. They didn't deliver what people needed them to deliver the software if it actually was delivered. um, Ended up not being what the final users expected. I mean, as the conference report itself said, they chose the phrase. The phrase software engineering was deliberately chosen as being provocative and implying the need for software manufacture to be based on the types of theoretical foundations and practical disciplines that are traditional in the established branches of engineering. Now, for all of those that do software, it's very different from actual engineering. Actual engineers have tons of references they can use. Like, for example, there are books with flowcharts that can help you select things like the steel that you're going to use in a boat. So that has to be different because it has to resist corrosion than the one you would use to make the girders in a building. So they have that, we don't. And the idea back then was, okay, let's try to turn this into engineering because that way we won't run into these problems. So, how is software engineering done? Nowadays, it's been almost 60 years since the term was coined, and mainly we don't do it. Why? There are two main reasons. Uh, Technology is constantly changing. We are all familiar with, like, for example, the very famous JavaScript framework of the week, where we get a new framework every week. So thankfully, that has kind of slowed down. But working in AI, I can tell you, is like a never-ending stream of new tools, new protocols, new things to try out and to test. And that leads us as a profession, as a field, into what I like to call fad-driven development, FDD. And on the right, you'll see a picture of Alan Kay. Alan Kay is a Turing Award winner. He is the designer of he's inventor and designer of Smalltalk. He invented object-oriented programming. He invented the Dynabook, which is basically what the iPad was based off of. It took basically that was in the late 60s, so it took about 40 plus years to go from this man's idea to the actual tech being delivered to people. And he has this very important thing that he said. So I think the lack of real computer science today and the lack of real software engineering today is partly due to this pop culture. Like, by pop culture, he meant precisely that we tend to like just go with the as engineers with the latest and thing that has caught our eye instead of having a reliable set of tools, methods, and that we reuse over and over again, like other engineers do. So software engineering has actually been very different during the time that we've existed as a field, that we've been actually building and delivering software professionally, so to speak. And I'm just going to walk you through a little bit through what that was like, so that you'll notice that AI is just the next step in a very long journey where very often things change. So the 1940s, uh, I'm picking this like at just kind of like arbitrarily, because this is when I think like we can say that programming started. Uh, in 1945, we had the ENIAC, and you can see there two people, Marilyn Weisskopf and Ruth Lichtman, which were some of the very first programmers, professional programmers, who who made a living at programming, and their job was basically rewiring the machine, like coming up with how the machine should be connected, how the hardware should interact, how the different modules of the machine should interact with each other in order to solve a particular problem. In this case, they were mostly solving uh, artillery trajectory solutions. And then in 48, we get what is called the Manchester Baby. That's not the official name, but it's called that because it was run in the University of Manchester in the UK. And that runs the actual first program that's stored in memory. That were 17 instructions. They were written in machine code, and the machine code was then inputted as binary. It's like ones and zeros. The person who put them in literally would type 101010, and that was the 1940s. That was what it was like. And in the 1950s, well, we get machine code and assembly for most of that decade until 1957, and in 1959 both Fortran and COBOL appear, and we start getting those high level languages which we are all now familiar. But the way you program, as you typed, yeah, your program using sort of like a typewriter, except instead of paper you were punching holes in a card, and that was it. Like, your program was a pile of cards that you took, put in, gave away to to the person handling the machine, to the team, because you didn't have your own computer, of course, and they so had a reader, and then they put the program in the machine and ran it, and then told you the output. And if there was something wrong, like it fell into a loop, or it gave the wrong result, or it crashed, they told you, hey, this is the output, and then you went back, thought about it, and like reprogrammed, repunched it, and rinse and repeat. Sort of like the same loop we work on whenever we program, but as you can see, there was tons of impedance, tons of wasted time. Just the very act of moving the punch cards around is super slow. And in the 60s, that changed. We get time sharing systems. You now can type, and it feels like it's your own computer. It's shared with many, many people, and but it's now kind of like gives the impression that it's yours, and that speeds up programming. That changes it, and we get Lisp and Lisp machines that introduces functional programming. It doesn't take off then, and by 68, that allows Engelbart, for example, to give the mother of all demos. There's a great video of that. I suggest, if you haven't seen it, you go see it, because it introduces the mouse, Windows, hypertext, video conferencing, version control, shared editing like you do in Google Docs. That was done. Then we had those tech back then, but it was programmed using punched cards. And in the 70s, that's where I think it really takes off. Programming, real the way that we do it today, sort of like kind of takes off. We get Unix in 71 and C in 72. As I mentioned, Alan Kay invents object-oriented programming in 72 as well. It doesn't gain traction. We used to do structured programming, and we finally get rid of the punch cards. We get the floppy disk in 1971, where those who never seen one, it looks like the save symbol, the save icon in most applications. And in the 1980s, personal computers takes off. You no longer have to actually share a machine that's remotely to which you're remotely connected to a console. You can actually have a computer, a real full computer on your desk. GUIs become common. OOP finally takes off with C++. And we have these tools called CASE, computer-aided software engineering. That think of it like computer-aided design in manufacture. And someone had the idea, hey, we can build similar things, use UML. And those, I don't think I've ever used one really professionally. So as you can imagine, those never took off. But we also get two very important things, like the GNU project is announced in 83 and the web appears in 89. So you can start to see that things are going to change even more in the future. Uh, Back then, everything that you programmed was for a mainframe computer or the desktop. Like there was no web, everything was local. You didn't have to worry about like the network and stuff like that, because it was all running on a machine or on a very controlled network. And in 90s, that changes. The internet and the web take off. We get those languages that we still use today: Python, Java, JavaScript. They come by 95. We have all three, and we get Linux. And for the first time, you don't actually have to pay for a compiler and an operating system, because you used to have to pay. I remember learning C back in the late 80s and early 90s, and I really really wanted to get my own compiler, except I couldn't afford it. I didn't have the money to buy it. And with Linux, it becomes available for free. And the open source initiative is formed in 98, and open source takes off. And that actually brings us and gives us engineers a bunch of tools that we didn't used to have, and that we can now play with and use for our own projects and not just professionally. And then in the 2000s, the Agile Manifesto appears. It helps replace waterfall as the most used development methodology. It used to be that you pre-planned the entire software development process project, and you sort of like took off and did it the way you, for example, would plan a bridge. The difference is, of course, that bridges, the civil engineers aren't asked to like move where the end of a bridge ends up mid construction. Like you can't do that. It's like you start and you know exactly where you're going to finish. That is not true for software. All of those of you who've worked professionally know that. And Agile helps change that sort of monolithic way of working, and we get a new methodology. And we also get TDD, test-driven development. It's popularized by Ken Beck. Ken Beck says I didn't invent it. It just sort of like rediscovered it. And it's true. It used to be done in the past, but Ken formalizes the practice, I think, and helps popularize it. Service-oriented architectures become popular, and we get AWS. The cloud appears. Like we didn't used to have the cloud. We used to have co-located servers. You owned and operated your own machines, even if they were nowhere near you. You still were responsible for that, and all teams needed to have ops people just for that particular task. And it's launched AWS with S3. This is the first service provided in 2006. And by 2008, you already have EC2. I remember using it back then. And you could do like professional grade work on machines that you didn't have to worry about owning yourself. And of course, Torvalds releases Git in 2005, and GitHub is launched in 2008. And in a matter of a year and a half, basically everyone is using GitHub for code. Like, for the first time, we have a place where we can share code easily, a centralized place where you can look for and contribute to projects. And in 2010, mobile computing revolution takes off. Phone in everyone's pocket. So that changes how we do development. Once again, our platform changes from the web to, okay, so now it's the web, but it's on these very tiny screens and it's touch instead of mouse, and now you have to worry about another whole set of things when you consider the capabilities of the mobile device are obviously much more limited than what you had or can have on a desktop machine or even a laptop machine. Uh, Cloud takes off really back then by I'd say 2012, and microservice architectures become popular. Well, the monolith starts to be broken down. We get Dora metrics are embedded in 2016, and those kind of like solidified the ideas behind the DevOps movement. And we also get containerization becomes popular. Containers go way back to like the I want to say the late 20 knots and the early 2010s. Uh, but they actually become popular with Docker and Kubernetes K8, which allow people to actually use them. So as you can see, like programming has changed massively. Like the platform we're targeting, the languages we use, the tools we use for those languages, how information is stored in the machines. It has changed basically almost every decade. And AI is just like the latest iteration of that. So, given all that churn, all that change, how do you become a great engineer? What does it mean to be a great software engineer? So, the things that don't change, you got to focus on that. The fundamentals, your algorithms, your data structures, your computer architecture and operating systems, and like learn a big O, both time and space is useful. Like yes, sorting, search, but also learn recursion and hash functions. Understand how dynamic programming works and how it's different from memoization and how memoization interacts with dynamic programming. There's tons of problems that use that. Uh, but don't stop there. Like go learn prim and Kruskal algorithms, Huffman coding, A star, which is like used for navigating mazes. That's like the most famous like AI algorithm out there. Topological sortness, pretty cool. Backtracking and bit manipulation. Like learn as many algorithms as possible and understand them and when they are used, because it doesn't matter if you were writing code back in 1950 or you're writing code in 2050. Some of you are going to be doing that. The algorithms are going to be the same, right? Those tools are eternal. They're math and they don't change and they're always useful. Same thing with your data structures, like arrays, trees, binary, B or B plus trees, or red black trees. Graphs, learn sorting, searching, and algorithms and graphs. Tons of problems actually can be solved and thought of as a graph. And knowing those algorithms is a huge help. Hash tables and stacks and queries, particularly priority queries, are also super useful. If you're doing anything with strings, do tries. And LRU caches are also very important, in particular because they are a great intro into caches themselves, which you will have to use everywhere. And of course, like pick one or two languages which you want to be really good at and check how those things, the algorithms and the data structures, are implemented in them. Because sometimes the theory will say, hey, no, this algorithm is better than this other, but implementation details will actually change which one is better. So be aware of that. And of course, you got to understand where you're running your code, how, what types of computer architectures are there, what the memory hierarchy is, vectorization and SIMD, what does that mean, and whether or not it applies to your problem, to the code you're writing. And of course, branching and multi-threading. We like to think the machines are very predictable, but modern CPUs basically just look at our code and go like, yeah, I'll do whatever I want instead of this. So sometimes it can be really surprising, and you can get some very nasty bugs, particularly around concurrency, or you might get some performance issues where you don't really expect them to exist, and that's because of the hardware you're running on. And of course, there's operating systems. Learn what the scheduler is, the security model, virtual memory. Most of you won't have to learn drivers, but if you're working with anything that connects to machine, any other kind of machine that or hardware that has to connect to a computer, drivers super important. Interrupts and file systems, and concurrency is it can fall like concurrency. You'll find it everywhere. It You'll find it in algorithms, you'll find it in data structures, you'll find it in architectures, and you'll find it in the following slide as well. Learn virtualization as well. And there's databases, SQL, NoSQL. Like I see now tons of people that don't know SQL. SQL is super valuable, particularly if you do anything in the ML space. Lots of the work there in AI and ML is actually working with data, and SQL is like one of the main tools we have. Uh, Learn the theory behind databases, like why do relational databases work the way they do? What is ACID? What is the CAP theorem? What are schemas and how do indexes work? Normal forms, what are those? What's the query planner and query optimization? Because like CPUs, databases, they will look at your SQL and or your NoSQL, and they'll go like, yeah, I'll reorder and rejigger and do my own thing. And you got to understand how and why they do the thing they do. Otherwise, you're gonna end up like chasing tons of performance issues, and that's gonna happen whether or not you're using AI or not. Networks, it also helps to understand how the network works. Like we now live in a world where all our applications basically use the network. Very few of the software you write will be desktop only. So learn the protocols, the OC layers. How does TCP/IP work? Uh, I'd take a particular look at UDP. It's becoming far more popular, and there are far more uses for it than we are exploiting today. It's gonna like I feel it's gonna like take off, and it's a great tool to have if you have a problem where TCP/IP just isn't cutting it, and topologies, sockets, and what REST means. And more importantly, I think you have to learn how systems work, how software systems are built. And for that, given the what I just said about networks and stuff is distributed, so understanding distributed consensus, synchronization, or Lamport, all the work by Leslie Lamport, uh, logical clocks, failure detection, the circuit breaker pattern, or how systems gracefully degrade, and why and how to time out, how to replicate things across the network so that it doesn't matter where your user is, they can access their information, and how that information gets updated so it's consistent, messaging, and how to actually monitor and observe something that's all spread out over the planet or the entire planet sometimes. And how do we actually design these things? Design patterns, both at the level of software, the code you're writing or that's being written, and the architecture itself. Like, how do you scale? When and do you scale horizontally? When do you scale vertically? How do you balance load? What's back pressure to design an API? How to share data? Caches, once again, super important, and security. Uh, in the following decade, we're going to get tons of work done in security. There's also formal verification. If you already know a lot of this, you can go into formal verification and study that. That's also something that in the future is going to like take off. And I'll talk about it a little bit later, maybe. So what else? Learn a language, learning well, and then learn a different kind of language. Like don't go from C to Python to Java to C sharp. Like those languages are basically all the same thing. Uh, Learn C, for example, to understand how the machine works. You say you use Python or JavaScript. Okay, fine. Learn a functional language. Learn OCaml. Learn Haskell. Learn a logical language. Learn Prolog. Just to know what kind of problems you can solve with those tools. Learning a different way of programming teaches you a different way of thinking. And that is an extra tool you have when you're solving a problem. Even if you're not going to end up using a functional or logical programming language, still knowing how to solve a problem using those approaches can help you more easily solve a problem using your most used tools. Uh, you will spend most of your time reading code. Like reading and reviewing code is super important. Probably more important than learning how to write code itself is how to analyze the things you are reading. And that means you have to understand the language, the syntax, the use cases, the limitations, what are the idiomatic expressions, how naming impacts, and how clean code actually looks like in your particular language and stack and coding style. Learn to debug. Printf, always a friend, but learn a debugger. Like understand how to use that to find issues, because as you will see, AI is not perfect, and you will spend a lot of your time babysitting the AI. Software engineering, understanding how teams work and how requirements are gathered, how to decompose tasks and assign them in a software project. That is particularly useful. DevOps also useful because sometimes you're gonna have to do that work yourself. And one of the most valuable things you can have as a software engineer is knowledge of a particular domain, whether it be UI, UX, visual design for data, where you're not, you also know about finance or health and the life sciences, logistic robotics. Bringing in that extra knowledge and that extra content actually makes you a far more valuable and powerful software engineer, because ultimately software is a social technical system. It exists and it's built by human beings to solve the problems of other human beings, and you need to understand what problem you're solving, and that means understanding the domain and what the problem is and why those people that you're working for want that problem solved. And so domain knowledge is super valuable for all that. And of course, soft skills. Uh, Work on communicating, uh, learn how to receive and give constructive criticism and feedback. You're not your code, you're not your systems. There are going to be some times where people push back technically. That's okay. It's not a reflection on you. That's one of the things you got to learn as an engineer. And it's like, yes, take pride in your code, but it's not you. Like, there's more to you than the output of your work. And of course, tooling. The command line is still valuable. Like we've got GUIs from since the 80s. The command line is still probably the most powerful way of interacting with a computer that we have. Case in point, where the cloud code get released. Command line. So version control, Git, Jiu-Jitsu, which is from Google. Those are very cool. There's also some other stuff that's being worked on by Microsoft, one in F Sharp, which I can't recall. But learn how version control works, become familiar with it, and you will have to use it. It will save you lots of pain. And Beacon ID, become really good at it. It doesn't matter which one it is, VS Code, NeoVim, anything from the JetBrains. Just become really comfortable using your tools. Familiarity speeds you up, and familiarity actually reduces the cognitive load while you're working, and not having to worry about, hey, how do I quit them? Uh, is actually a great help when you're actually trying to solve a problem that is not actually quitting them. So Docker, yeah, virtualization is important. Um, we are moving into a world where most of the stuff that runs will run in containers in one way or another. And also learn about the cloud. And for that, you got to understand networks and distributed systems. So that's why I mentioned those. And understand cloud engineer, learn a single cloud. You don't have to learn all three or all four, and because the services are pretty similar between each other, and you will just have to learn a little bit of differences between one and the other when you switch. But knowing how things work in depth, how these things are actually built and operated behind the scenes, will save you also tons of issues. Like serverless is not actually serverless. Like there's an actual machine running things, and understanding that can help you, pick, uh, decide or not, you actually want to go serverless or not. Your use case actually will benefit from that, and you can only do that if you understand how it works behind the scenes. So learning that how to use it and how it's built helps a lot. Same thing as learning how the CPU works. It's like, where is your code, where is my code running, where is my system being operated, where are the limitations it has to work within. So how we do software engineering, how we go beyond just vibe coding. I mean, you've all probably seen vibe coding. When it started, you probably saw all those people saying, hey, yo, I don't know anything about programming, but I built my application in like a week. And a week later, those same people were saying, hey, people are stealing my API keys. Someone messed with my database. This thing is super slow. I don't understand why. Because they don't have the fundamentals. They understand what the machine did, what the model generated. And for that, there's no cure but going and actually getting those fundamentals. So there's no best model. Uh, you got to work on pick the one that suits you best. The top of the coding leaderboard is constantly changing. Uh, you should focus on finding a process and a workflow that works for you. One where you feel the most productive, one where you end up with the least amount of bugs, one where you create what you want to create in the most comfortable way possible. Planning, like all of those fundamentals, they turn in our use, particularly when planning. Use reasoning models for that. Aid yourself of those. And there are also tools like Taskmaster to do system design, plan out development. That's where you learn how to break down tasks, because you don't want to be doing things by one. You want to like give a whole bunch of agents, uh, a bunch of tasks, and then just be checking on them as they work along and as they do the work. But in order for you to be confident that they're going to do what you need them to do, you got to give them a good plan. For coding, as I mentioned, tools like Codex and Jules, which came out like last week, uh, spread out the tasks, write and run tests, and just do code review. Uh, Particular recommendation: leverage AI to do code reviews as well, but do them also yourself. Like always check all code by yourself, manual check, and use different model for generation and review, because it will find the mistakes. A different model will find the mistakes of the other far more easily. Um, your job is now to verify the functionality and quality of the code that the AI produces. And you need to know and understand the code base, because we're shifting up the abstraction ladder. Even if you're a junior engineer, the expectations on you around designing code and designing systems are going to be much higher, because writing the code itself, it's valuable, but the AI can do that if properly prompted, if properly directed. And it'll be your job to decide what it should do. And for that, you need to understand system design, and you need to understand what the code base does, how the system is set up together. And for that, you need to learn how to read code. So that's where reading code becomes super important. And then This is particularly if you're doing your own startup or have a side project that you want to take live. Deployment and operation, like use agents to monitor your CI/CD pipeline, to analyze your logs, to like do security audits. If you're part of a very small team, these things will speed you up tremendously, and these are things that you really, really want to do, and that usually kind of fall off of the wayside once once you actually are building stuff at speed if you're a small team, because there's no one that can actually take that the slack and do that. So that's AI. That's a great job for AI. Key takeaways. So software engineering is a field that's constantly changing. Like AI is just the next change that happened. uh, be adaptable, be eager to learn new things. And that's one of the coolest things of our job, that we get to keep on learning all our lives, or all professional lives, and trying cool new stuff. And but also don't be like fat driven. Like learn to find what the best tool for the job is, and be really good at using those tools. Fundamentals, they take you a long way because they don't change, and those are both like CS and tech. Uh, they are also soft skills. They are also domain knowledge. Those things are super valuable, and once you put them together, those fundamentals will take you a very, very long way. And the other thing is, you're in control of the AI. I mean, the AI does what you tell it to do. We're prompting them. They are following our designs. They are doing the tasks that are assigned to them. The quality of the system, the output, the solution is your responsibility. The AI is just doing manual work. You are actually doing thinking. You're the brains behind the operation, and as software engineer, that is your main job, to be responsible. So that's it. Thank you very, very much for putting up with me and hearing what I have to say. Um, I'll take any questions that anyone might have. Okay. Where does one start with learning the fundamentals need to become a great software engineer? So, if you study computer science, you're ahead of the game. If you didn't, okay, so what do you do? Uh, Algorithms and data structures. Do those first, and then probably move on to system design, and then from there on branch to what is important for the kind of projects you want to work on. Distributed systems, if you want to work in really big projects that you know have to have users all over the earth. Um, if you want to make games, you probably want to study graphics and learn maybe a little bit of math for that, and also how the CPU uh, actually does things. And so yeah, that's it. Where does one start? Wait, learn. Oh, okay. How does one select the best tools? Okay. Uh, Tool selection. And as I said, I mentioned Codex and Jules. Those didn't exist like 3 weeks ago. And it's hard. Tools change constantly. As I said, select stuff that fits the way you want to work, the way that feels most comfortable, and select stuff that automates away the parts that you don't want to do. Cost is important, particularly if you're selecting for a team or for a company. But the consideration there is then, okay, so which one is the one that has the best community? Languages don't win in popularity because they are the best at a particular thing, or because they're super or have tons of features. They win because they have the best community. Same thing with libraries, same thing with other tools. Like community is super important. If you are like have two options and you don't know which one to follow because they both kind of look good, one has something that the other doesn't, and vice versa, pick the one with the best community, the one with the most vibrant community, the one with the one that has more contributions, the one that you feel like you fit in best as a member of the said community. and pick that one because that is super important. So that is how you choose tools, and obviously you have to like keep up to be aware of what changes are coming, what new tools are being released, but don't feel the pressure to like change your workflows every single week. Like just focus on solving the problems, and if the tools at hand are good enough, they're good enough. Okay, any further questions? Oh, how is AI going to change? Oh, how is AI going to change software engineering in the next 5 years? So now we have this fleets of agents. So what's going to happen is we are actually going to become um, the people who actually break down the tasks for a big feature, assign them, and then monitor a whole bunch of agents all working at the same time on different parts of that feature, on different parts of that problem. And it becomes our job to organize that, to manage that, and to make sure that all of it together makes a coherent whole that actually solves a problem and does it with in a way that fits with the architecture of our system and fits the style of the code in the code base. You're ultimately responsible for the quality of that work. And so that is where the job is going. It's going more to design, it's going more to making sure about code quality, making sure that that the system is secure, that data privacy that is maintained, that all regulations that you might have to operate under, that your product might have to operate under, are followed. You're going to have to focus on those things and actually solving the problem and making sure that the solution is good from a technical perspective. Not so much in writing it yourself, but in directing and organizing the work of the agents, the AI agents, doing that. Where also I think is going to help a lot, it's going to be in the formal verification of systems. Right now, we don't do that because it's tons of math, it's slow, and changes break whatever proof you wrote. So, as we saw, we moved from waterfall to agile because we had constant changes because it's possible with software. And if it's possible, people will ask for it. And AI helps with formal verification a lot. Uh, so they're actually, for those of you who know Terence Tao, the mathematician, who's one of the best mathematicians alive today, he, he's working on formalizing lots of math using uh, proof. It's a theorem prover and associated language called Lean. It's in the fourth version, Lean 4. And that kind of work is going to impact directly on our work because once we can prove that something actually does the things we claim, that the code actually is correct, that it doesn't have bugs, because mathematically we can prove that, then we start really moving into the engineering part of software engineering. We now have tools that we can trust 100%. We now have code that we know absolutely is correct and will do what we want it to do given the parameters upon which it was built. And there's work from I can't remember, someone at the University of Chicago, a professor there. They are they invented the area of proof repair, and that is the next step in that chain where you make changes, it breaks your proof, but now we have a way, and with the aid of AI, a much easier way of proving that our new changes actually didn't break what we didn't want to break, and that they actually do the things that the change is supposed to do. And once we get that, software becomes a far more engineering like discipline. So I think that in the next 5 to 10 years, we're actually gonna start doing software engineering for real all the time. And any further questions? No. Okay. Thank you very, very, very much, and have a good day.